Hey, you guys. We'll move your reference there, see if anybody gets it. Number 4, we're back, week number 6. This is some good stuff. I love complex numbers. 4A, part 1. Express each of the complex numbers Z1, Z2, and Z3 in modulus argument form. Okay, Z1 will equal 2 cis pi over 6. I'm not going to explain these. If you want, you can pause the video, check by drawing a triangle in the appropriate quadrant, and then go ahead and confirm whether or not your answer is good to go. All right, Z2 is 2 cis 5 pi over 6, and Z3 is 2 cis negative pi over 2. You could have 3 pi over 2 as well, and that would work. No problem. All right, number 2. Hence, show that the points in the complex plane representing Z1, Z2, and Z3 form the vertices of an equilateral triangle. Okay, I'm going to do my best here. Might not be perfect, but that's okay. Oh gosh, try that again. All right, cool. So Z1 is extend 2, rotate pi over 6. There's Z1. Okay, so this length right here is 2. All right, Z2, extend 2, rotate 5 pi over 6. There's Z2. This length right here, also 2. Z3, extend 2, rotate 3 pi over 2, or you could extend 2 and rotate negative pi over 2. That length right there, also 2. Okay, so back to geometry. This is some good stuff. If this angle is equal to this angle is equal to this angle, then each of these chords from Z1 to Z2, Z2 to Z3, Z3 to Z1, and Z2 to Z1 should all be equal in length. I forgot to write Z3 here. But there you go. You've got yourself an equilateral triangle. Okay, let's move on to Z3. Let's move on to part 3. Goonies, by the way, movie reference. Here you guys. Show that Z1 to the 3n plus Z2 to the 3n is equal to 2 times Z3 to the 3n. Okay, so let's work that left side there. Z1 to the 3n would be 2 to the 3n cis 3n pi over 6. Okay, I'm going to erase this. We'll work this on the left side. We're going to show it equals the right side. Okay, plus Z2 to the 3n. Of course, I'm using Demov's theorem here. 2 to the 3n cis. That would end up being, what is that? 15 n pi over 6. Okay. So let's reduce these. So this would be 2 to the 3n cis pi over, n pi over 2 plus 2 to the 3n cis, well, let's see, 15 over 6 reduces to, oh gosh, is that 5 n pi over 2 And now this is kind of cool, but maybe you're not as thrilled with this as I am. Those are coterminal. Therefore, I would then have 2 to the 3n cis n pi over 2 twice. All right, I've got 2 of them. All right, if those 2 red angles are coterminal. Okay, and now I can show that this piece right here is equivalent to z3 to the 3n, then I'm good to go. So z3 was equal to 2 cis negative pi over 2. So z3 to the 3n would equal 2 to the 3n cis negative 3n pi over 2. And now I've got exactly what I want because n pi over 2 and negative 3n pi over 2 are coterminal. And, whoops, n pi over 2 is coterminal with negative 3n pi over 2. Therefore, z1 to the 3n plus z2 to the 3n is equal to 2z3 to the 3n. There you go, guys. All right, let's move on to part B. All right, it says for us, state the solutions of the equation z to the 7th equals 1. I'm going to do the initial setup. 1 is equal to cis 0 plus 2 pi k. All right, I'm going to go ahead and put all the solutions up here, so I'm going to go off camera for a second. Why don't you try that, and then when you're ready with your answers, you can come ahead and press play and check with my answers. All right, here you have it. I've built this z sub k, which is cis 0 plus 2 pi k over 7. Right? I take the 1/7 power to both sides. The modulus is 1, so 1 to the 1/7 is still 1. So using de Moivre's, I divide the angle by said number, and it builds me this generator. So I get cis 0, 2 pi over 7, 4 pi over 7, 6 pi over 7, negative 6 pi over 7, negative 4 pi over 7, negative 2 pi over 7. So there's part 1. All right, let's look at part 2. If W is the solution to z to the 7th equals 1 with least positive argument, determine the argument of 1 plus W. Express your answer in terms of pi. Okay, so this answer, right, this z with least positive argument would be the following. Let's call it W, where W is going to equal cis 2 pi over 7, right? That's our least positive argument right there. Okay, so it says determine the argument of 1 plus W. Okay, so let's consider this. W has a real component, and it has I times its imaginary component. So if I take 1 plus that, that's 1 plus W. Okay, now all I'm adding 1 to will be the real component, not the imaginary component, right? So my real component has now changed to this. Okay, so let's graph W real quick on a complex plane where the angle right there is 2 pi over 7. 2 pi over 7. Therefore, this would be the cosine of 2 pi over 7. This would be the sine of 2 pi over 7. Should be a 7. Okay, now what we're going to do is we're going to draw the same graph, but it's going to be 1 plus W. So here was the point W. And the next one, we're going to draw 1 plus W. Might be like, whoa, what just happened there? Well, I'm going to take 1 plus cosine of 2 pi over 7. And nothing's going to change with the sine of 2 pi over 7. This is still the sine of 2 pi over 7. Okay, so that means if I were to overlay these, this is 2 pi over 7, and this is some other angle right here. Let me do it in yellow. We're going to call that angle phi. Okay. Now, what are we trying to solve for? Express the argument. Okay, there's the argument. That phi value is our argument. So our argument of 1 plus W is equal to phi. So let's do a little work with what we know about trig. Okay, so the tangent of phi is equal to the sine of 2 pi over 7 over 1 plus cosine of 2 pi over 7. All right, let's use a trig identity, both top and bottom. Let's use double angle for sine on top. So that'd be 2 sine of pi over 7, cosine of pi over 7. Okay, because sine 2 theta is 2 sine theta cosine theta. So theta would be pi over 7. Good. I got that. I hope you did too. If you didn't, slow it down. Okay. Now, in the denominator, I'm going to have 1 plus double angle for cosine. So that'd be 2 cosine squared pi over 7 minus 1. So the 1's will reduce. This is kind of crazy, guys. It's a bit crazy, but it's, well, fun. Okay, so what you'll see will happen is the 1's reduce here. One of the cosines reduces in the bottom and the other in the top. And the 2's reduce. So what I end up getting is sine of pi over 7 over cosine of pi over 7, which is tangent pi over 7. Oh, this is cool. Hey, now look at that. Look what you can now do. Tangent of one is equal to the tangent of the other, therefore phi is equal to pi over 7. That is awesome. Okay, so that's part 2. Let's get on to part 3. Part 3 says, let's see here, show that z squared minus 2z cosine 2 pi over 7 plus 1 is a factor of that polynomial. Okay, state the other 2 quadratic factors with real coefficients. Okay, so I'm going to go to a very foreign factoring place right now, and I just want you to hang with me as I do it. I don't know that I wanted red, so I'm going to switch my color here. I'm going to go blue. Z squared minus 2z cosine 2 pi over 7 plus 1 can be factored, you guys. I'm going to try to squeeze it all in there. But it would be z minus cosine 2 pi over 7, z minus cosine negative 2 pi over 7. Okay. I think we can agree that we would see z squared and negative 2z cosine 2 pi over 7. But let's multiply cosine, negative cosine 2 pi over 7 and negative cosine negative 2 pi over 7. Okay, so let's do that over here. Negative cosine 2 pi over 7 and negative cosine negative 2 pi over 7 would be cosine squared, oops, whoa, big fail, fail, Mr. Lud, fail. This should be cis, I believe. Nope, that is cosine. Okay, that's cosine, but these are cis. Okay, and if I multiplied cis negative 2 pi over 7 and cis negative or positive 2 pi over 7 times cis negative 2 pi over 7 using de Moivre's, I want to erase. Here we go. I would get negative 1 times negative 1, which is positive 1. I would get cis, and then I would add those angles, which is 0, and cis 0 is 1. That's where I get my 1. Okay, now those two angles, Z1 and Z6, they're complex conjugate pairs. They're conjugate pairs. And roots of any polynomial, this polynomial, z to the 7th, has 7 roots, and it's got 3 pair of conjugate pairs. So it's only got one real solution. And then it's got 3 separate pairs of complex solutions. And you can see them show up there. So it's asking us state the 2 other quadratic factors with real coefficients. So in addition to this quadratic factor, okay, there's the only real factor, which is z0, which is 1, right? Then we have what would end up being z minus cis 4 pi over 7 times z minus cis negative 4 pi over 7, as well as our third quadratic factor, which would be z minus cis 6 pi over 7 times z minus cis negative 6 pi over 7. I'm going to expand those real quick. That would be z squared minus 2z cis, oops, I'm sorry, that is cosine 4 pi over 7. Okay, and the reason it's not cis is because the even odd identity on cosine and sine will make the sine part, the imaginary part of both of those, disappear, because one of them will be negative and one of them will be positive, so they'll negate each other. So you only get negative 2 cosine 4 pi over 7, and then of course you'll get plus 1. Okay, so there's my second quadratic factor, and then the third quadratic factor would be negative or z squared minus 2 cosine 6 pi over 7 plus 1. So your factors, you got 2 there, you got 2 there, you got 2 there, and your last one is z equals 1, your only real factor. That's a beast, you guys, but it's an awesome problem. Obviously, between parts A and B, that looks like 18 marks. So you got probably 22 minutes or so, maybe 23 minutes for those 2 problems. And I'm thinking that, accessibly, you might be able to get 10 to 12 marks and feel pretty good about moving forward with that. So I hope it went well. Let me know if you got any questions. And as usual, I'm always available. Shoot me a message and we can chat.